Today we're talking about scale drawings. A scale drawing is a proportional two-dimensional drawing of an object. So an example of that could be blueprints that architects draw up when they do floor plans for houses or buildings. Maps are another example. A scale model is a proportional three-dimensional model of an object. So examples of scale models are globes or model vehicles if you have like a model train or a model car. When we are talking about scale drawings and scale models, we use this word scale a lot. Scale is a ratio that compares the measurements of your drawing or model with actual measurements. So if you have a drawing or a model and 1 inch on that drawing or model in real life is equal to 3 feet, this 1 inch to 3 feet would be your scale. It's a ratio comparing your drawing or model to the actual. A scale factor is another word you might hear. Scale factor is basically a scale written without units because the units are the same. So if I had this scale 1 inch to 3 feet and I changed them both to inches, so it was 1 inch over 36 inches, 1/36 would be my scale factor. What's nice about a scale factor is it also tells me that my model or my drawing is 1/36 the size of the original. So let's take a look at some examples here. So we're going to start with the scale drawing. So I have a small map here of the state of Michigan. And when I look at this map, I see that it has a scale in the corner already. 1 centimeter is equal to 50 miles. So I'm trying to find the distance between the two towns of Cadillac and Detroit. So I've already drawn a line between those two towns and measured it, and it was about 3.5 or 3.5 centimeters. So I know that the scale for the map itself is 1 centimeter equals 50 miles. And the distance that I'm looking at is 3.5 centimeters, and I'm trying to find the actual distance. So I'm setting up a proportion here. And now I can use my cross products to find the answer to this proportion. So I'm going to multiply across. So 1 times x gives me 1x. 50 times 3.5 is going to give me 175. So x equals 175 miles. So the distance between Cadillac and Detroit in reality is 175 miles. Now let's say we're making a model of the layers of the earth, and we know the liquid outer core of earth is 2,300 kilometers. I want to know how thick should I make that on my model. My model is going to have a scale of 1 inch equals 500 kilometers. So I already know the scale. That's going to be my first ratio. I also know the actual outer core is 2,300 kilometers. So I'm always comparing my drawing or model to the actual. So the actual is going to go down here on the bottom, and here is my unknown. So I'm going to multiply across here. So going this direction, I have 500 times x, or I can just write that as 500x. And the other direction, I have 1 times 2,300, which equals 2,300. So if I divide each side here by 500, I get 4.6. So I actually want, on my model, the layer of liquid outer core to be 4.6 inches. A scale model of the Sergeant Floyd Monument is 10 inches tall, while the actual monument is actually 100 feet tall. And we want to know what is the scale of the model. So we know that the model itself is only 10 inches, while in reality it's 100 feet. When we're finding our scale, this could be our scale, except we want to reduce it. So we're going to divide both of these by 10, so we'll have 1 inch over 10 feet. So every 1 inch on the model stands for 10 feet in real life. Now, if we want to turn this into a scale factor, we need everything to be in the same units. So we've got 1 inch to 10 feet. I'm going to change them both into inches. Since there's 12 inches in a foot, I'll multiply by 12 here. So 1 inch is actually equal to 120 inches. So my scale factor is 1 over 120. The model of this monument is actually 1/120th of the size of the actual monument. For our last one, we're going to look at a scale drawing of a computer chip. Computer chips are very small, so when we do our scale drawings, they're actually going to be bigger so we can see all the components of the chip. So here we have a blown up computer chip, and it had a scale of 1 centimeter to 2 millimeters. I know that it's blown up because the 1 centimeter, the first number in my ratio, is larger than the actual. And I measured each side of this chip on the drawing, and each side was 4 centimeters. So it was a square with each side being 4 centimeters. So they want me to find the perimeter and the area of the actual chip in the drawing. So first I'm going to do the perimeter. So each side of the chip in the drawing was 4 centimeters. So to find my perimeter, I'm going to do 4 plus 4 plus 4 plus 4, or 16 centimeters. The next thing I'm going to do is the area. Since it's a square, I can use side squared or length times width to find my area. So 4 squared, I'm going to get 16 centimeters squared for my area. Now they want me to find the perimeter and area of the actual chip. Well, before I can do the actual chip, I know that on the drawing each side is 4 centimeters, but what is that in reality? So I'm going to have to set up a little proportion here. So I know that my scale is 1 centimeter is equivalent to 2 millimeters. And my sides are actually 4 centimeters in the drawing, so I'm trying to find this number right here. Well, I can see that 1 times 4 would give me 4, 2 times 4, this value is going to be 8 millimeters. So in reality, the chip is so small that each side is 8 millimeters long. So now I can find the perimeter of my chip. I'm going to add 8 plus 8 plus 8 plus 8. These numbers make it seem like it's bigger, except remember we are now measuring in millimeters. So that's only 32 millimeters. That's 3.2 centimeters, so it's definitely smaller. The area of our chip, since each side is 8 millimeters, is going to be 8 squared, or 64 millimeters squared. So that's 6.4 centimeters. The last thing that we're being asked to do here is to compare the ratio of our perimeters and our areas to our scale factor. So first let's figure out our scale factor. Our scale was 1 centimeter is 2 millimeters. Remember, a scale factor, they need to be in the same units. So I'm changing them both to millimeters. 1 centimeter is worth 10 millimeters. So I've got 10 millimeters to 2 millimeters, which I can reduce to 5 over 1, and I can get rid of the units since the units are now the same. We're going to do that same process with our perimeters. So in our drawing, the perimeter was 16 centimeters, and the actual perimeter was 32 millimeters. Now before I do any other work, I'm just going to reduce this guy to make it easier for myself. So I'm going to divide them both by 16. So I have 1 centimeter to 2 millimeters. Now remember, a centimeter is worth 10 millimeters. Now I can reduce and I can get rid of my labels since they're the same. So it reduces to 5 over 1. And it's the exact same ratio as our scale factor. Now let's take a look at area. For our area, we had on our chip an area of 16 centimeters squared, and that was on the drawing, sorry, and in actuality 64 millimeters squared. Well, once again, I'm going to make this easy on myself, and I'm going to divide these by 16 and reduce them a little bit before I go any further. Now, area is a little bit different because area is a measurement squared. So we want to take out this squared. So if I take out the squared, 1 times 1 would still give me 1 centimeter squared. So this one isn't going to change. But if I take out the squared here, this had to be 2 times 2. Because 2 times 2 would have given me my 4 millimeters squared. So I've now taken the squared out. I'm going to change this into the same units. So I'll have 10 millimeters for a centimeter and 2 millimeters here. And I can get rid of my units because now they're the same and I can reduce. So I will have 5/1 squared. So this part of my ratio is the same as my perimeter and my scale factor. It's just a little different because area has a squared.